Hello, this is Mr. Waters. I'm sorry that this is coming to you so late. I've been having technical problems this afternoon and this morning. But anyway, so here is our lesson here, and it's going to be on paired data. And as it happens, this is probably almost certainly going to be the last new material we're going to have before the AP test, right? Now, on the subject of the AP test, tomorrow around this time, I'm going to be attending a webinar from the College Board, and they're going to be telling us, and me and maybe some of your other AP teachers, they're going to be telling us how the AP test is going to be conducted. All right. As of right now, though, you know literally as much as I do if you've gone to those links to the College Board that I put under the last day's module, Monday's module. Okay, so if so you could go check out those links if you want to find out where we are right now. But anyway, so here's the new thing for today. It's about paired data. Okay, here is the situation. Here is the scenario. All right, that we're working on here. Previously, we've been working, or in this unit, we've been working with two sample data. That means we've been doing the very common and important inference situation, and we want to compare data from two populations to see if there's a difference in their responses or a difference in the parameter in the population, right? Okay, so for instance, it could be the mean weights of 10-year-old girls in the U.S. versus, it could be the mean heights of 10-year-old girls in the U.S. versus the mean heights of 10-year-old boys in the U.S. Or it could be the mean weights of 10-year-old boys in the U.S. versus 10-year-old boys in India. Or in which case, our parameter of interest would be a mean, right? Or it could be something like voting habits. We were interested in making inferences and making comparisons about the difference in voting habits between, say, white likely voters and Hispanic likely voters. In which case, we might ask, is there a difference in the proportion of white voters who are going to vote for candidate A, likely voters who are going to vote for candidate A, versus the proportion of likely voters among Hispanics who are going to vote for candidate A, right? In that case, our parameter would be a parameter of interest. And the reason why we would be, the parameter of interest would be the proportion of voters among whites and among Hispanics who are going to vote for candidate A. And the reason why we call that a two sample or a two population situation is in order to make the comparisons, we're calculating or collecting two independent samples from each population, right? And then calculating a sample statistic from each population, and in order to make the comparison, comparing those two sample statistics. So here, we'd calculate a sample statistic from population 1 x bar 1 and a sample statistic x bar 2 from population 2, sample 2, and then the difference that we would be interested in, that we would be making inference about, is the difference between those two separate means. Or if it was a population proportion, we'd calculate a p-hat from population 1 and a p-hat from population 2, and we'd be in order to make the comparison, we would calculate the difference between those two p-hats, those two sample proportions, right? And anyway, in short, a two sample or two proportion situation looks like, well, literally there's two populations and there's two samples, and you're making one measurement, a single measurement, independently and separately from each population. It could also be an experiment where you've got a sample of volunteers, and you split the sample for one treatment. One half of the sample gets one treatment, the other half of the sample gets the second treatment, and in effect they're like two populations, all the possible people who would get treatment 1 and all the possible people who would get treatment 2. And then your comparison, the inference you're making, is the difference between the responses to those treatments, right? Still a two-sample situation. Okay, now, on the other hand, there's a lot of situations where you're working with what are called paired data. And as you will see, paired data are actually one sample and one population situations. In the scenario of paired data, you're collecting one sample, right? And each individual in the sample has two separate measurements made on them, right? It's not two samples, one measurement. It's one sample, two separate measurements. Now, what's the difference? Well, the difference is how we calculate the sample statistic. In this case, let's say we had a sample with individual 1 and individual 2 and individual 3 and individual 4, right? And about individual 1 and 2, about each of the subjects, we make a measurement, some kind of measurement. Doesn't matter what. So let's say measurement 1 was 2, 3, 4, and 5 for our subjects, and then about each individual, each subject, we made a second measurement, 10, 11, 12, and 13. Now, we're not going to take the average of those two measures separately and then compare the averages. No, what we're going to do is we're going to subtract each individual and find the difference in responses or the difference in the measurements for each individual separately. So for individual 1, the difference was -8, and for individual 2, the difference was -8, and so on, right? So as it turns out, they're all -8. So what we end up with here, as I've circled, isn't two sets of measurements, but actually one measurement that is the difference for each of the subjects. So this is our sample, right? This is our sample data right here, are the individuals. These the individual measurements for the two measurements, the individual numbers for the two measurements aren't part of the sample data. They're differences of the sample data. Of course, we can take the mean of that, which, since they're all -8, would be equal to 0. So this is why this is a one sample situation. Superficially, it looks like a two sample situation because you've got two sets of numbers. But actually, the difference is the fact that we've only collected one sample, and we end up with only one set of sample data, which are the difference. Is in this case, we would say x bar d would be equal to 0, right? Because they're all -8. So when we do inference, for this one, we would use one sample inference. A one sample z-test for proportions, or a one sample t-test for means, or a one sample t confidence interval for means, like we were doing in Chapter 8 and Chapter 9, rather than the two sample procedures we've been doing in this unit for Chapter 10. Now here is an example. Okay, I'm going to cover this up so that we don't see everything all at one time here. And I want to see this. Hopefully that's not too small for you to see. It says, the developer of a new filter for filter-tipped cigarettes claims that it leaves less nicotine in the smoke than does the current filter. Because cigarette brands differ in a number of ways, he tests one filter on each cigarette from each of 9 brands and records the difference in nicotine content. His results are given below. Now, you understand, this is what's called a matched pairs scenario. Okay? And the reason why it's a matched pairs is there's really only one sample. That is, these 9 brands of cigarettes that are supposed to represent all the brands of cigarettes in the world, of which there are many, 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 right? But about each brand of cigarette, so each of these brands of cigarettes, that's the subject, that's the individual, as it were. About each brand, he makes 2 measurements. Now, strictly speaking, since you can't smoke the same cigarette twice, he actually burns 2 different cigarettes. But since each cigarettes, we're going to assume they're identical, in effect, the 2 identical cigarettes will stand in for one individual. And we can gauge the difference in their responses that way. Okay? So here they are, and these are the old filter nicotine content of the smoke, and this is the new filter nicotine content of the smoke in milligrams. Okay, so now what we're going to do here is we're going to calculate two things. We're going to construct a confidence interval for the mean difference at the 95% confidence level, and then we're going to do a significance test. We're going to ask, does this sample give evidence that the new filter really does reduce nicotine at the 0.05 significance level, at the alpha equals 0.05 significance level, right? Now, so confidence interval first. Okay, so here I've calculated just right off, I've calculated what the sample data is. Remember, for matched pairs, the sample data is going to be the individual differences. So here, that's the difference from old nicotine to new nicotine, old filter nicotine to new filter nicotine for brand A, which is 0.7 minus 0.6 is 0.1. And then here it is for brand B, for brand C, and so on. So this list here, this is the sample data for the matched pairs test, not the individual measurements up there about each of the two individual filters. Now I used one var stats on the calculator, and I got that the mean of these differences is 0.189, and the standard deviation of those differences is 0.127. I literally put these into L1 on the calculator, and it told me what the means were, okay, and what the standard deviation was. So this is the sample mean, that's the sample standard deviation. So now we go down here. So now we would want to state the problem. By the way, from now on and on your AP test, if you're doing any kind of inference, either calculating a confidence interval or conducting a significance test, even if it doesn't prompt you, you'll always follow all four steps, right? Even if it doesn't say, follow the four-step method, it probably won't, but you'll just do the four-step method automatically. Okay, so stating the problem, we did that already. We're constructing a confidence interval. So step 2, we're going to plan. Okay, so since the parameter of interest was the mean difference of all of the between brand A and between filter A and filter B for all possible cigarette brands in the world, we're calculating our parameter of interest as a mean, our sample statistic was a mean, so we're going to calculate a one sample t interval for means. Why a t interval? Well, number one, we've got no idea in the whole wide world what sigma would be for the population of all possible brands in the world. And not only that, the sample size is small, it's only 9. So either way, we're going to have to do it. If we're going to be able to calculate this confidence interval at all, it's going to have to be a t interval, right? So now we what do we do now? Oh yeah, we go ahead and we test the conditions. Number 1 up here, a random sample was implied, so we'll go with that. Number 2, we're going to say that 9 cigarette brands is way, I'm going to guess there's hundreds of cigarette brands around the world, so 9 is less than 10% of all of them. And now, since we don't know sigma, and we don't know anything about the shape of the population of different mean differences, right? And we don't know, and the sample size is small, it's not bigger than 30, what we'll do with, in order to know that we can really do our t procedures, we go ahead and we make a little plot here of the sample data. So I took each of these and I put them on a cute little dot plot here, right? And you can see here that that's pretty symmetrical, about as symmetrical as 9 sample points are going to get, and there's no strong outliers. So what we get from that is simply the idea that since the sample data are relatively symmetrical, we can infer that probably, therefore, the sampling distribution of all of the mean of all the differences is also approximately normally distributed. So therefore, we can go ahead and use the t procedures. So I wrote it right there. T procedures are allowed. So anyway, now we do it, and that's this bit down here. Okay, so our confidence interval is x bar, the point estimate, right? And then plus or minus t star, okay, the critical value that goes with a 95% confidence level, and then the standard error for this sampling distribution, standard error, because we're going to use the sample standard deviation, there it is, in order to estimate what this, as an estimate of the population standard deviation, of the population standard deviation. So now we go ahead, x bar, that's our point estimate, 0.189, so that goes right there. T star, well, I looked up, we said over here that there were 9, the sample size is 9, so the degrees of freedom were 8. So I looked up on the T table for degrees of freedom 8 and a 95% confidence level. It turned out that the T star from the T table was 2.306. So that goes there. And here is the standard error, 0.0127. The sampling sample standard deviation divided by the square root of 9. And that works out to be 0.014, right? So that's the standard error. So I plunk those into the formula here, and I get 0.189 plus or minus 0.032, which gives us, which is one way to write the confidence interval, or a slightly better way is 0.157 up to 0.221. Now I didn't write it out, but of course we interpret that, right? We are 95% confident that the true actual difference in old filter nicotine versus new filter nicotine content for all possible cigarette brands around the world is between 0.157 and 0.221 milligrams, right? Okay, so now, that wasn't specifically asked, this part, but you notice that 0 is not in that interval. So if we were asked, we could say, well, this is strong evidence that there really is a difference in the nicotine content of the old filter versus the nicotine content of the new filter, because if there wasn't any difference, 0 would be somewhere in an interval, which it's not. Okay, very good. So that is a confidence interval. Okay, so let's see now. Here's what the significance test would look like, and I'm going to cover up most of it again here so we're not confused by a whole bunch of stuff. So the significance test here, we're asking what I had on the other page, is there evidence? Does that sample give us evidence that there really is a difference between the nicotine content from the old filter versus the nicotine content of the new filter? So here's our parameter of interest, the mean difference in nicotine content for the two filters in all cigarette brands. Here's our two hypotheses. The null is that the difference is 0. Now, it's not like mu1 minus mu2 is equal to 0, because we're not comparing two populations. We're saying our one sample were all those mean differences, right? And we're doing that because there's really only one sample, right? There's only one sample of cigarettes that we're doing this with. Okay, and then the alternate is that there's not a difference. So mu difference is not equal to 0. So this, as you can see, is going to be a two-sided test, and at the significance level of 0.05. Well, alrighty then. So we're going to plan. It's a one sample t-test, check conditions. We won't do that again. It's exactly what we did for the confidence intervals, including making that little dot plot to make sure that that the sampling distribution really is normally distributed, or approximately normally distributed. So we'll count that as done. Now we do, and we calculate the test statistic, which is the z of the differences. Okay? Well, we see here that the x bar difference is 0.89. The null hypothesis was 0, so we go there, and the standard error was still 0.14, which is the same standard error that we calculated for the confidence interval. Divide, and oh look, it's 13.5. Well, I don't even have to look up on the t-table to interpret a p-value for that. Okay, 13.5 is far beyond any of the t-values that you would find on the chart. They all end up at about 3.5 maybe. So 13.5, if you look up on the t-table, that would give us, in effect, a p-value of 0, even if it's two-sided. Technically, we'd multiply 2 times 0, but it's still going to be 0, right? Okay, so what's our conclusion? There is strong evidence. Okay, so we have strong evidence to reject the null hypothesis. There is strong evidence that there is a difference in the nicotine content of the smoke for the old filter versus a new filter. Notice, and this is important, I didn't just say reject the null. I say, yes, there's strong evidence to reject the null, but I explain what rejecting the null looks like in context, because this is what we want to know. Does that make sense? Okay, is that answer right there. Very good. So I think that's enough for this example. Okay, I'm going to put out another example now, and I'm going to put it right here. And here is the second situation, and I'm not going to continue the video here. I'm just going to zero down on it so you can see it. Hope you can see it here. I'm also going to post this under classwork so you can print out a copy of it. And you are going to do what we just did. Okay? Tai Chi is often recommended as a way to improve balance and flexibility in the elderly. Below are before and after flexibility ratings on a 1 to 10 scale. 1 being, or rather 10 being the most flexible for 8 men in their 80s who took Tai Chi lessons for 6 months. Now, hopefully you can see this is paired data, because there's one sample of individuals, right, and 2 measurements, and in this case it's like a before and after measurement for the two, for our sample of 8. Now, what I would love you to do here is to calculate a confidence interval for the difference, for the differences in the flexibility rating after Tai Chi versus the flexibility rating before Tai Chi. And remember, the higher the number, the more flexible. So a bigger number is better, right? And so you're calculating what a confidence interval for the average improvement, I guess you might say, in the flexibility level for all old men in their 80s, right? And then you're going to calculate you're going to carry out a significance test at the 0.01 level. Does this sample give evidence that Tai Chi, a course in Tai Chi, will improve flexibility of men in their 80s? Alrighty, very good. So that's that. And I will put the answer, I will post this problem here plus the answers in a little while. Also, some other classwork that I would love you to do, and then the homework too. Toodaloo.